Ladies and gentlemen, welcome to the this morning's Sunday session. I know Sundays are meant to be a quiet time, but let's get all rowdy for Nic Crouch.
Good morning, everyone. A quick review of Python and graph databases. I'm going to start with who I am, because it is sort of important to the context of the talk. I'm a consultant at Deloitte Melbourne in our information management division. We do data in our division. We do digital web design, all that sort of stuff in our other consulting divisions. We do security in some of our other work. We're always looking for good people. Come and talk to me if you're looking around. Plug done. I'm a recent grad of Flinders Uni, and in my last year there, I looked at graph databases and sort of used one, and I published some research on that. But otherwise, when I submitted this talk, I didn't have the talk ready. I didn't have the material ready. This talk is as much a learning journey for me as I hope it will be for you. With that in mind, how many of you are familiar with the idea of a graph? Awesome. So how many of you can then divine what a graph database might do? Cool. All right. So for those of you who don't know, a graph is essentially a set of objects connected by links. So you start with some objects, you add some links, you add some more links and some more objects, you add one more, you've got a graph. If I switch between terminology, the objects can also be called vertices, nodes, or points. The links can also be called edges, arcs, lines, or relationships. I guarantee I will switch between terminology. I might even call edges vertices, and for that I apologize in advance. So before I go too deep into this, this is sort of inspired by a lot of work that's been done at previous PyCons and around the place on the internet. These slides will go up, so you can take a look at these later. We stand on the shoulders of giants. So today, an exploration of graph storage using Python. And what I mean by that is I didn't have time to go and learn the individual languages and APIs of every single graph database that's out there. They're not at the point where we have a SQL-esque standard. So anytime you want to start using a new one, you might have to learn a new language. Had I gone and done that, this would be a radically different talk, and I'd probably cover a lot less. So with that in mind, the API must be Pythonic for me to bother looking at it, or at least in this talk. Sort of graph.execute language doesn't count. I'm learning, did very little configuration. I downloaded the tar, I untarred it, and I ran start.sh. That generally comprises the extent of my configuration for this, and I'll touch on that later on. So yeah, no configuration, no tuning. My testing was on a single AWS node, so you're not going to get a good idea of what happens if you try and scale it across, a bazillion nodes. I can't answer that question. It would take me lots more learning to work that one out. So the simplest way to set up a graph database is create a class called node, create a class called relationship. You may not even have to do that. Set up some dictionaries and track the relationships between your objects. Pretty sure we've all done this at one point or another. If we've spent more than 10 minutes in Python, you might not have called it a graph, but that's essentially what it was. Obviously, there are problems with that. You're going to have to maintain it. It's not going to be consistent across all of your different code bases. You will have different use cases for different things, and you'll customize it accordingly. And there's no persistence. So your computer turns off, your graph goes away. That's very easy to solve. Use self. And so instead of dictionary, you import shelf, and now you have a persistent dictionary of nodes. It's actually reasonably quick, given. You've still got all the other problems, though. So, quick off topic, NetworkX. I used it a lot during my testing. I would call it the Python graph library of note. Not the subject of this talk, still awesome. So, graph databases. Essentially, there's one big one. It's Neo4j. If you've heard of only one graph database, you've heard of Neo4j. OrientDB, you can sort of see on there, has been tussling with Titan for a little while. When I looked at this graph, Orient was on top, Titan was slightly behind. But yeah, Neo is the dominant force. I'm going to take a look at the top 3, starting with the incumbent. So Neo was first released in 2007. It's a Java program. The licensing is a bit weird, but not unfamiliar to you if you've been around in open source for a while. It's your GPL for Community Edition and commercial otherwise. They've previously been, or at least there's references to them being AGPL licensed, which brings with it all of the benefits and drawbacks of that approach. And essentially, you've got a server, and it gives you a REST interface to which you can submit queries. The Python libraries I'll be looking at do exactly that. Otherwise, you can use a language called Cypher. Cypher, whether or not Cypher is a good language depends on how much you like ASCII art to me. Obviously, I'm talking to a Python conference, so we like explicit instead of implicit, and we like long, I forget the Zen of Python now, but we like longer, more communication rather than less, essentially. And to me, Cypher is a bit, it's a bit ASCII art for me. That's personal preference. Yeah, easy to install, untar, run, go. There is high availability in the Enterprise Edition. Obviously, I wasn't using the Enterprise Edition because I'm not filthy rich. Apparently, it's not as scalable as one might like. So you get redundancy, but you don't necessarily get sharded processing. So from Python, you've got a range of options. Python-au is the official driver. They're all REST clients because that's what Neo exposes. Neo4j REST client is sort of, I guess, before Python-au, there was another library, and then that went away, and so Neo4j REST client attempts to emulate what that did, sort of as a drop-in replacement. You've got a couple others. Bulbflow is particularly interesting, even though I sort of didn't cover it in this talk, because it can actually connect across several databases. So this is what you get when you load up Python-au. You set up a graph connection, which is reasonably obvious, and then with that graph you start creating nodes and relationships. This is a fairly obvious pattern, and it differs in detail across libraries, and I will go through those changes. It's a little bit personal preference, but it's fairly obvious. Like I say, I don't really want to run through code, so the slides will go up later. So, good. It's simple. Going back, this is all fairly obvious stuff on one pass of the documentation. And it is reasonably well documented. It's easy to connect, it's easy to get started. I had very few problems connecting using this one. And it's got some cool little edges. It's got spatial, it's got a spatial library, which I really wanted to spend more time with, but does take a little bit of getting into. and you've sort of got to know the library itself back to front before the spatial stuff's going to be very interesting to you. Not so much is, I say skinny API on the slide, and what I mean by that is that it's not, yes, you've got node creation, you've got node deletion, you've got relationship creation and deletion, this is all good. You can even chuck in a great many nodes and relationships in a single transaction, and that kind of works, assuming you don't pass it too much. But there's no transaction support past a single line of Python. So you can't say, for example, with transaction as tx, do this block of code. You can only do that with Cypher. So that to me was actually a little bit disappointing, because there's lots of things where you sort of want to do a little bit of processing on the nodes in between creating them and committing them. And it's the same sort of thing as you would see in SQL. You know, there are times when you want that transactional control. And as far as I could tell, python-au doesn't actually give that to you, only if you use Cypher. It doesn't give you much, it doesn't give you much ORM support. So yes, you can say, here's a node and here are some properties on that node, and that's fine. But unless you go and install a third-party library, which sort of wraps around python-au, you don't get your Django-style enforced representation in the database, which makes sense because there's no, it's not a schema. There's no schema on a database or on a graph databases. You just have lists of properties on each node. So the ORM is on the Python side, and it's for your convenience rather than for the necessity of the database. Neo4j REST client, apart from having a really long name, it's very similar. You give it a username and a password separately instead of in the connection string. And this I found kind of cool. There's some Python hackery is the word that comes to mind. I'll call it wizardry. That lets you essentially, instead of is related to, you can give it any relationship name in here, and that's what label will go in the relationship in the database. So that was kind of cool. Also kind of cool is the reusable query, query object, I suppose. You can build those as large as you like. You can then cache them in your own memory rather than trying to get the database to do it. And then you can just pass it to filter functions as necessary. You'll get your elements. One thing I did notice, you do have to index the elements because it gives you the whole thing. And it often gives you, it will give you exactly what you ask for. It'll give you a list of nodes that meet your criteria. Often in my testing, I only ever wanted one node, so that's what I did. It does have transaction support with a context manager, and that's nice. However, there's the asterisk, and the asterisk is kinda. I think it's supposed to work. Maybe not. I like the filtering syntax. I like the labeling syntax. And I liked lazy evaluation of queries. It is still REST because we're still connecting to Neo. Neo only has REST. So performance. Relative numbers here, because again, no tuning, no effort at all went into making this performant. I did, however, go to some trouble to make it consistent. So they're relative numbers. And I've also sort of done something in Postgres with SQL Alchemy, so you've got a bit of a basis for comparison here. And you can see that for the small stuff, the REST client is quicker marginally than python-au. But then when you get to the big stuff, it balloons out. And I am reasonably sure that's because there's a lot of string processing happens trying to, in both of these libraries, trying to munge whatever you've given them into valid cipher. And when you give them a lot to deal with in short order, that's string processing. And I did profile this, but not really scientifically. That string processing starts being the majority of your issue. I think Python-EO's put some effort into optimizing that. Like I say, it's not tuned, completely unoptimized, and like I said, consistent hardware, consistent algorithm implementation. For the record, the retrieving implementation is graph specific, so I started in one node and then proceeded to get the rest of the graph via a breadth first search. So it's a pretty standard traversal that just gets everything. And yeah, this is what you get. Python-EO is not orders of magnitude worse than Postgres, and given some tuning, given some expertise, I'm pretty sure you'd get a lot better than Postgres. Certainly, Python-EO is not. It's at that range where I would say, yeah, if you've got the business case, you could make it performant. OrientDB, released in 2011. They don't market it purely as a graph database. They market it as a graph database and a NoSQL database, so a document store as well. It's got lots of stuff in there. It does scale across multiple servers. It does support SQL of a kind. It does have an OrientDB driver for Python. That's a binary driver, which is cool. I didn't test it because one of the rules was it can't just be execute other language. And that's all you get with the OrientDB driver. So then I skip right on to Titan. Titan, released in 2012, written in Java, Apache licensed, which is kind of cool. And you can switch amongst storage backends. Those are the three sort of big ones that they talk about. I'm pretty sure there are more. And they have Hadoop integration, which is kind of cool. Yeah, so you can also do search backends. I'm pretty sure for the benefit of our sponsors, I'm pretty sure Elasticsearch is the, I want to say the default, but I could be wrong there. And it's built for scalability. It does have commercial support. Aurelius used to do this. DataStax now does this. This has happened in the last 3 to 6 months. It looks like DataStax are going to try and build their own commercial graph database out of the Aurelius team. That'll be really interesting to watch. I don't know what's going to happen to Titan. So with that in mind, Titan and Python, there is a driver called Mogwai, written by Cody Lee. It's really, really Pythonic. It's actually kind of cool. It's written by someone. He presented this driver. It was in the list of talks earlier. He presented this driver at a PyCon. It's got lots of really cool stuff in there. And okay, I slipped this slide in last minute. It uses RexPro. RexPro is the binary driver for the Tinkerpop stack. The Tinkerpop stack, I just want to brush over, aims to be at least an open source graph database standard. So sort of like SQL is for relational databases, Tinkerpop aims to be, and Gremlin specifically, aims to be for the graph database area. Their documentation is extensive but dense. It's sort of one of those projects where you get an excellent one-liner and pages and pages of fantastic-looking technical documentation, but nothing in the middle that sort of says, and this is what we do in a couple paragraphs. There's a lot there. It's been around a little while now. The guy who works on bulbs, which I sort of mentioned earlier, works on Tinkerpop. There's a few of them that work on it. it's really cool. I'm not sure how, certainly Titan implements it, but I'm not really sure that it's gaining a lot of traction. I'd like to see it gain traction because it is cool. So, performance on Mogwai, not great. I saw, this is sort of double what I saw with python-au on the short end, but on the large end, it's not as bad. Certainly, it's not ballooning up to 50 minutes like I saw for the Neo4j REST client. I'm interested that loading takes 9 minutes, which is sort of still in the range of python-au, but then retrieving stuff takes ages. I'm pretty sure that could be because Titan does some indexing for you for the search. And when I'm doing my testing, I'm just chucking it all in there and then getting it all straight back out again. So that could be related to the fact that Titan is doing some indexing in the background, but I'm not sure. Either way, you can scale Titan, which you can't necessarily do with Neo4j. So if that's an application you've got, this can decrease very quickly, I think. So what should you use? If you're looking at the sort of the big three, Neo4j, if you've got the cache, if you are doing enterprisey sort of graph database work and you can justify the business case, you can get Neo4j to help you, and I'm sure it will become very performant. You will probably also at that point put the effort and time into learning Cypher, because then you will make it very performant. Titan has got the benefit of scalability and Hadoop integration. When I say Hadoop integration, I'm not 100% certain if it's Hadoop integration in the sense that it can grab stuff off HDFS, or if it's Hadoop integration in the sense that it actually sends out MapReduce jobs. But it does scale. There was a talk at this year's PyCon that talked about the way, and I think it's the New York Times, uses this in production. However, they don't use Mogwai, they use their own, essentially sending gremlin queries straight through. And then Orient, again, if you're happy to use their language, it is well supported. You can see exactly what you're going to pay on the front page. And it supposedly scales well. Haven't got Python to vouch for that, but I have read that it scales well. Obviously, all of this is, again, this is a journey of learning for me, and so it should become a journey for learning for you if you're looking seriously. How am I doing for time? 5 minutes? Awesome. So, Python graph databases. This is a bit of fun for me. Essentially, what we're looking at here is graph databases that are implemented mostly in Python. GraphiqueDB, unfortunately, I found 2 or 3 days ago, so I haven't really been able to test, but it does look very cool. You've got a multitude of storage backends that you can use. It is one guy. Neither of these, by the way, are anything you should be letting anything near a production stack. And in fact, this is a direct quote from the documentation page for Adu. Be careful. So, yeah, but they are both under active development, and they are pure Python. And when you pip install Graphique or pip install Adu, you get everything you need to run, certainly Graphique, you get everything you need to run a server, a graph database server. And then you can jump into that source code and play around with it all you like. And it's all Python, and that's cool. But yeah, it's beta quality, it's alpha quality. Adu is Python 3, which is also cool. And I should cover, I'm pretty sure everything I've said, everything I've talked about today is Python 3 compatible. I think the Neo4j REST client may only be Python 2. But I'm sure you'll find out when you try and run it on Python 3 if you do. So a little bit of Adu. you tell it where you want it to put a Berkeley database. If you've got a distribution that has Berkeley database installed and set up and all, it's a set of libraries all for you, that's great. I don't think Ubuntu Server has all that stuff installed by default, and I had some trouble making it. In fact, I think the reason for that is licensing. It is Oracle, and Oracle is fun. So yeah, lots of those distributions you will have to go and apt-get or yum install or unzip. You get transaction control. You can, and this is not the only way of creating transactions. There is a context manager that works reasonably well actually, and then you have to do everything inside one of those transactions. It works as far as I've seen. It's reasonably performant. That's not really fair because it is still file-based technically because it's Berkeley DB. But it works. I haven't broken it yet. I have no doubt that if all of us tried on Monday and Tuesday, we would break it horribly. But yeah, no, it seems to have worked relatively well. So, graphs are awesome for lots of things. You all pretty much you all knew what they were, so you know that already. Neo4j, Titan, Orient, upsides, downsides, and if you want to have fun, try Adju. And I can't guarantee that Graphique is fun. It might actually be really awful to get running. I haven't tried at all, but they look fun. Thanks.
Thank you. Oh, here we go. Yeah, better. Thank you, Nick, for that talk. Does anyone have any questions? If you have, please come up to the front. Oh, bit of exercise, never hurt anyone. Huh? Anyone else who wants to ask a question, please form a line. Excellent, thank you.
Hi, yeah, about that, basically that standard, that open source standard called Tinker something. About it, basically, how does it play with standards for IoT out there? So how would it connect the whole of the internet together? Does it have any provisions for that?
I'm not 100% sure I understand the question. So in terms of IoT stuff?
So the thing is that basically there are going to be a lot of different machines all around the internet with their own different concepts and different ways of how to describe those contexts and different things that are connected together.
Sure.
Right? For example, a warehouse would have its own different basically components in it, and how those components are built, they would probably link to the manufacturer, and the manufacturer would say that, okay, this component is built out of these ingredients and whatnot. So this is like more or less defined in some way, and there are standards for it out there. But the Tinker standard, does it basically incorporate these things? So does it aim to be that big or
not that I've seen. So essentially what it is, it gives you a set of standard interfaces, essentially. So Gremlin is the standard language. It's kind of based on Groovy. And then Rexter, or I'm using a lot of names here that are actually incorrect. There's Tinkerpop 2, which has all the different names, and then Tinkerpop 3, which has new names that I haven't got yet. But yeah, so Rexter is the method of supplying a REST interface. RexPro is the method of supplying a binary interface. And in theory, if all the graph databases were to implement those interfaces, then we would just be able to switch them in and out as required for our applications, almost like what you can do with relational databases. So not really is the answer to your question, I suppose.
Okay, cool.
You talked about labeling nodes with various properties and things. Can you label the vertices similarly and add attributes to
Absolutely.
with all of them?
Yes.
Okay.
Some of them are a bit nicer in how they do that than others, but it's all roughly the same. When you query them, you end up generally getting a dictionary.
Okay.
You mentioned that PostgreSQL was significantly faster than many of the solutions, and then you went on and made recommendations that didn't include Postgres.
Right.
And now you're asking about adding attributes. Well, you could certainly do that in an RDBMS. And I guess what's the rationale for using a graph database instead of a relational database to achieve all of this?
Excellent point. Okay, so the benefit of relational databases is that lots of work in tuning them has gone in over 30 odd years or so. And so you get great numbers like what we saw. And the reason I say, in fact, all three of those, if you want them to be performant, you're probably going to end up paying for support because somebody with expertise is going to have to tune them for you. Whereas Postgres, you can stand up and you get great figures. And the reason I say, and I sort of brushed over it, but I said if you've got the business case for these, then you should use them. The problem with relational databases is that they're generally meant to get sets of data, and graph traversals tend to be grab one, grab one, grab one. And if your indexing is right, that works okay. I've seen instances where they don't necessarily work at scale, but again, not a lot of work had gone into tuning that either. So I guess the answer, I should do the short answer first. The short answer is you should use Postgres if you don't have the business case to investigate and have someone come in and work on a graph database. As far as I'm concerned, relational databases are sort of the default. So I guess I don't recommend it because it's the default. If you are looking to get into graph databases, then those are the three that you would look at. They work. Postgres works. Obviously, Postgres works. Lots of people use it.
My question's kind of similar, but not quite. You keep talking about this business use case and all of that for graph databases.
Sure.
So what are you using graph databases for? What would you consider using them for? And what kind of data or queries and problems are you trying to solve with this technology? So
there are two problems I've previously used Neo4j for, never in real production. So the first one is I worked in an organization where we had stock, and essentially we were trying to track what happened to bucket of bolts X, bucket of widgets, and then we put in widget box X and widget box Y into a process, and they came out as widget box XY. Then we would split up widget box XY into widget box A, B, and C. So what we wanted to do was track how much of widget box A came from widget box X at the top. Yeah. The other one I've done, and I have used this, again, not in production, but for research, was tracking academic papers. So essentially looking at, here are the authors of these papers and how they link together, and here are the citations between papers and how they link together, and then how can we apply some cool graph data mining algorithms to find information from that without having to reload the whole thing every time. Cheers.
Oh, thanks for all your questions, and let's give Nic a final